So as we just saw, in order to use the Kingman equation, the requirement is that the utilization of the resource must be less than 100%, which means that there's enough capacity to meet all the demand on average. But now we need to adjust what we learned about flow rate in order to include the effect of variability in queuing. Because remember before we said that the flow rate was equal to the process capacity, where we assumed we have enough raw materials as input and we had plenty of demand so that our bottleneck was working 100%. But as we saw, that means as soon as there's variation in the system, the queue in front of the bottleneck working 100% will just go to infinity. So let's adjust our definition for flow rate. We take out the assumption that there's high demand and that the bottleneck has to be working all the time, and change to a more realistic situation where the flow rate is determined by the minimum of either the process capacity, which is our bottleneck, the input rate, or the demand rate. Now, here I think we also will still say that the demand rate is sufficient. This could become very important if you're moving lean production back up into your suppliers, as we'll discuss a little bit later. But right now we're looking at the trade-off between the process capacity and the demand rate. And let's say our demand is 8 skateboards per hour, right? We have a process capacity of 10 skateboards per hour. So this gives us then a flow rate of 8 boards per hour, where the demand rate is our limiting factor. So now we have to recalculate the resource utilizations. So for example, at assembly, the resource utilization becomes 8 over 12 or 67%. At sand, it's 8 over 15 or 53%. And finally, at our bottleneck paint, it's 8 over 10 or 80%. So what do we notice? Paint is still the bottleneck. It has the highest resource utilization of all the steps. However, because the demand is lower than the capacity, the utilization is now less than 100%, which means that we won't have a buildup of a queue when there's variability in the system. On average, we have plenty of capacity in our process, even at the bottleneck, to process the demand. But what really happens? So, now, we have the situation where our utilization is less than 100%, so we can calculate the average waiting time in front of paint. Now, remember, with no variation, there's no waiting. Paint just works. In fact, in this case, it wouldn't work 100%, but there'd be no queuing in front of paint. However, with variation in the arrival and processing times, then we can calculate our average waiting time as 6 minutes, processing time factor, plus times 80%. Hang on. Erase this. 0.8 divided by 1 minus 0.8 times, and our variability factor, we're going to use the same as before, 1.2, which is actually quite high. And here we end up with a T wait of 28.80 minutes. So, in the case with variability in front of our bottleneck resource, even if the bottleneck resource has enough capacity, there's a significant waiting time. Now we want to look at this a little more carefully because there's a lot of interesting information here. Here we have a graph of utilization from our resource going from 0 to 100%. And we're showing on the y-axis our waiting time, which we've gotten from our Kingsman equation. And this is also equal to the non-value added time in our system. During that waiting time, nothing is being produced. The inventory is just sitting there doing nothing, waiting to be processed. So, first of all, we want to look at the case again with no variability in the system. So do you remember paint? When there was no variability in the system, even when paint was working 100%, there was nothing queuing in front of it. We had a 0 wait time in front of our paint, even at 100%, for this case where there was no variability. However, draw this in a different color here. When you have variability in the system, then what you see, your waiting time at low utilizations is also low, but at some point it increases exponentially. And as we saw earlier, if you go to 100% utilization, it is theoretically goes to infinity. So with variability, there's an exponential increase in the wait time with increasing capacity utilization. And if the variability increases, the curves will start to look like this. And again, this is kind of an artist's rendition here. But here we have increasing variability. So what we see here then is at low utilizations, you have maybe some waiting time, but only at high variabilities. Essentially, the waiting time is still very low at low utilizations. But as you increase utilization, at some point, the waiting time starts to become significant. And as a rule of thumb, this is sort of roughly around 80% utilization. You start to find that your waiting times are becoming a problem. So this is a very important result. And in terms of lean production, we're looking at this waiting time as a non-value added time. It's just a waste. So how can we reduce the waiting time? Well, we've got our 3 factors. One thing we can do is reduce the processing time, P. How can we do that? Well, if we do a process improvement, we eliminate the waste in the process itself, or we improve the process, then we can reduce P and reduce our waiting time. Additionally, in our utilization factor, well, we can keep the utilization as low as possible. This brings the U over 1 minus U factor as low as possible, and again, keeps our waiting time then low. Of course, if you've got expensive machines that you want to use, have a high utilization, want to use them as much as possible, this becomes a trade-off. But again, as we saw, above 80%, the utilization curves tend to become very significant, and you tend to have a high waiting time. Finally, you could reduce the arrival variation through perhaps scheduling slots, or appointments, as you see in a doctor's office. For example, you reserve tables in a restaurant, or even now they're scheduling rides in amusement parks. You could also try maybe to smooth the demand. So you have high demand in a certain part of the day. Well, then you make your prices at that part of the time of the day higher than at the other parts of the day. Process variation, that can be reduced, for example, with standard work, as we'll see later, so that processes are standardized and clearly written down so that there's less variation with the process time itself. And what is the significance then on lean production? Well, again, we can look at these 7 wastes, and we understand now that waiting is one of the most important wastes, because even if we have enough capacity in our system, waiting will occur in any real system which is subject to variability. Waiting increases our flow time, inventory builds up in queues in front of processes, in front of resources, and importantly in this lecture is that we see how critical utilization is on our wait time. High utilization means that we're increasing the non-value added waiting in a process. And this means, again, that we have to keep our eye on our bottleneck where the utilization is the highest.